going to move to the industry side of things. And we will have Paul Schuler come and speak. So Paul is the Director of External Affairs for the Americas for Oil Spill Response Limited. He was formerly CEO of Clean Caribbean and Americas, and he is a recognized expert on international aspects of oil spill preparedness and response, in particular on the science and use of dispersants to combat oil spills.
Well, thank you very much. I'm following some great presentations and learning quite a bit. So it's a pleasure to be here. I changed the title a little bit because it's not only about science, but in the response side, it's about the technology that supports the science as well. So if there are things you may like to do, but if you don't have the technology to accomplish them, which is pretty much the case in Deepwater Horizon at the beginning, and I'll show you some things that have changed since. So I'm going to talk about science and technology. Well, I like to start out with saying that there's been quite a bit talked about the area contingency plans. And a couple days after the explosion at Deepwater Horizon well, we were mobilized and we flew from Fort Lauderdale over to Gulfport, Mississippi, and started doing spray operations. And when we did this, and I'm not sure a lot of people are aware of it, we had a designated oil to dispersant oil ratio. We were trying to hit 1 to 20. Which comes out to 5 gallons per acre or 50 liters per hectare. This was based on the oil slick being 0.1 millimeters, which is generally what an oil slick gets to after about 12 to 24 hours. So where did this come from? And the reality is that there was a lot of science leading up to Deepwater Horizon that was incorporated in the area contingency plan. And Mr. Wenner said it's the area contingency plan is kind of the Bible. So this was not a cavalier thing to do. It was a planned thing to do. And if there was a spill tomorrow, there are plans to do pretty much the same thing with some changes based on things that were learned at Deepwater Horizon. So when you have a spill, there are only about 5 or 6 things you can do, and these are them. This is our toolbox. You can monitor, which in some cases is all that's need to be done. There are some things that happen simultaneously, like source control, which is not necessarily responding to the oil, but trying to stop the flow of oil. And then these other things, containment or chemical dispersants, burning, shoreline cleanup, those are our tools, and that's all we have, and that's what we're going to be pulling out of the toolbox. Generally speaking, all of them. You know, there's one or two that may predominate, but generally speaking, at some point for a large spill, they all get used. What drives it? Well, certainly one thing is what is the science and technology, what's the available resources to respond to a spill. But the other things are the health and safety of the community and responders, the feasibility, sometimes the weather or geography or logistics infrastructure prevents you from doing things. As Brad mentioned in his 5 questions, our first question is always what kind of oil, because that's going to determine what you can and cannot do. Resources at risk is very important. That also determines what priorities you're going to do things on. Available resources. I looked at the map you just showed of the area contingency plan, and I say, yeah, that's kind of neat that you got all those booming lines there, but where are you going to get the boom from? So that's an issue. Some of these other things, net environmental benefit analysis, I'm going to talk about in a moment as falling back to Brad's talk again about Dr. Spock there. And most importantly, you have whatever you choose, you have to match your response with the resources and with the scale of the oil spill. So you'll see certain things, and one of the reasons we get driven towards dispersants is that mechanical recovery simply is not going to make that big a dent in a large oil spill. So this is my analogy of Dr. Spock. How many of you have heard of the tropics experiment? Whoa, wow, that's better than most times. So this started back in 1984, and this is one of the seminal studies that determined the concept of net environmental benefit analysis. It was an area in Panama that had coral, seagrass, and mangroves in close proximity, and there were 3 areas studied. One is a reference area about a mile away. The other was some oil this was pure crude oil, was spilled, and this area had dispersed crude oil. And you can see the pure crude oil stays on the surface, goes in and oils the mangroves, gets stuck in the substrate, does some damage to the seagrass and the mangrove. But generally speaking, the trade-off here is that the oil on the surface doesn't impact the coral very much. The trade-off when you disperse the oil is that the oil goes into the mangroves, but because it's dispersed, it tends to come back out. It doesn't adhere to the roots. The seagrass gets on the crustaceans in it, or invertebrates get somewhat damaged and have mortality. But you can see in this case now you have the coral has some exposure to the oil. So this is the typical trade-off that we deal with in looking at net environmental benefit analysis. And as we look further at the use of dispersants, you'll see that that's a trade-off. It's the water column versus the shoreline. And I'll talk about in a minute about Deepwater Horizon. So based on the fact that we have science available looking at these kind of things, there were decisions made back in the 80s to design a system for putting in the back of a Hercules to spray during a spill, to spray dispersants. Now, if the science wasn't there, quite honestly, we wouldn't have this system. We're only going to buy equipment and capabilities that we know are accepted and can be used. If it can't be, then there's no point in us having them. This happens to be a training exercise we did off of Fort Lauderdale in December of 2009, where we loaded what's called the Airborne Dispersant Delivery System in the back of a Hercules, and we used to fly with the Coast Guard a lot as well up at Air Station Clearwater. We went out off the coast of between Miami, Fort Lauderdale. We had a spotter plane practicing spray on, spray off, all the sort of things we did. And we did the exact same thing on April 24th, 2010, which instead of flying off the coast, we flew up to Gulfport, Mississippi, and we began an 83-day deployment where we had 80 sorties flying over the Deepwater Horizon area and generally spraying between the Deepwater Horizon well area and this shoreline in this area here. We also have a stockpile of dispersants, and again, we wouldn't have it if it wasn't known to be approved. So it's on the National Contingency Plan product schedule that EPA is in charge of maintaining. What are the relative advantages? Well, here's the typical trade-off: a slick on the surface or dispersed oil. With being on the surface, the wind vector is what generally drives it ashore. And if it's in the dispersed into the water column, you remove the wind vector and generally prevent a lot of the oil from going ashore. This was exactly what was done in Deepwater Horizon, where there was a political decision to preserve the shoreline, and it might be a different decision at a different kind of shoreline, but the Louisiana shoreline is very sensitive and they're losing a lot of shoreline, and the marshes, as we heard earlier, is a high sensitivity. So by dispersing the oil out here, you remove the wind vector. Here's the current vector. Remove the wind vector and it tends to prevent a lot of oil from going ashore. That's what was being done. Then you're looking at a couple of 3 weeks to see that dispersed oil gets into the food chain in terms of bacterial colonization, and it works its way up. So over the course of a couple of 3 weeks, we have biodegradation take place. Everybody, I'm not going to spend much time on this, but we do know all the chemical components of dispersants. This is not intended to be a dispersant talk, and we have stockpiles of it. And we have a global dispersant stockpile with dispersant in the UK, in Bahrain, in Singapore, Rio, and Fort Lauderdale, so that we have enough to do what I'll talk about more of, subsea dispersant injection for up to 30 days. So these are just some of the concepts that we look at. Again, I don't want to go into these too deeply, but the key is to look at that trade-off when you're either looking at what we call net environmental benefit analysis, or the new term is spill impact mitigation assessment, actually not analysis. So what I think it'd be, I've done some of these workshops with Monica and the Sea Grant team before, and I was trying to decide what's the best message to leave you. And I think I could talk about SEMA for a long time. I could talk about NEBA, I could talk about tropics. I can also talk about how dispersants work chemically and physically. But I think one of the best things to leave you with is what would a spill look like, and what a dispersant's role in a spill. Because I think sometimes we're so caught up with trying to message some of the ways we think and develop strategies that we fail to look at the big picture. So let's just take a look very briefly about a subsea well blowout, or what we call a loss of subsea well control. And so you're going to have the oil come out with quite a bit of energy generally and create a plume at some particular area, usually about 200 to 300 to 4,000 feet above. You get a trapping layer with fine particles. The large particles, large droplets go rather quickly, and you get surface expression here. These smaller droplets may be entrained in the trapping zone for a long time. And in the Gulf of Mexico, there's an oxygen-rich layer of Antarctic current water at the bottom, so there was some aerobic degradation here. That's a good thing. But one of the things we get up top is a high level of VOCs, volatile organic compounds. And those right up top is where the workers need to work to try to control this well, or drill a relief well. So a combination of factors is one of the reasons we like to do this subsea injection, which is to target the dispersant right at the wellhead, is to knock down those VOCs so people can actually work up here and shut in this well. It's a major consideration in what we do when there's a subsea blowout, of which there haven't been many. But this is the Deepwater Horizon taken from a satellite. I talk about scale. You can see this is a skimming vessel that ran through here, not really in the big picture doing that much, which is why with the surface expression, we're looking at using dispersants to break this up before it gets too close to land or sensitive resources. These are all the folks working above the well, trying to do a variety of things to control that well. And needless to say, the VOCs in the atmosphere that they're working in is going to either, if we do subsea dispersant injection, a lot of the VOCs dissolve on the way up, and we look at a lower VOC environment and a better place for them to work. If the VOC environment atmosphere gets very high, everyone needs to go into special PPE, and the work is going to just slow down or stop. I mentioned you saw the picture of the Hercules spraying the dispersant on the Gulf of Mexico. Since Deepwater Horizon, our company has taken two 727s and converted them to spray aircraft. So this is kind of the next generation. The idea is that they can get places quite a bit faster. And we're a global response organization. So we keep our two 727s based in the UK, and basically they can go anywhere in the world rather quickly. And in places like Brazil, and the Gulf of Mexico, actually, where you may be going out 200 miles, the ferry time is quite long in the Hercules, which is pretty much of a slow mover. So what I'm saying here is, once you have an incident, you're going to have some surface expression of the oil coming out of the well, and the area contingency plan and the variety of plans there are to allow you to drill and operate. Pretty much at this point, say, get dispersants out there. It's because we can get out there quickly on day one, day two, in order to get the mechanical recovery equipment going. The logistics are days, and again, not quite as effective. Ultimately, you're going to see all of those tools brought into play. So let me just walk you through a little bit, and I'll do this rather quickly, of what a response would look like. So we have a subsea well. Here's the blowout preventer, which failed in Deepwater Horizon. The first thing we need to do is a survey and figure out what's going on and see if we have access to the BOP. One of the good things that happened in Deepwater Horizon was the platform and all the structure fell away from it and not on top of the wellhead, which would have been another problem altogether. So you take a look at this. The next step would be to, once you have access, and we have equipment to use local ROVs, but do we have tools for cutting and debris removal, clear the way so that we have access to the BOP. So the second thing we're going to do, and all this time we're talking about a release of oil, is to see if we can put some equipment down on the sea bottom that gives us the power necessary to do a BOP intervention and try to shut the BOP. If it works, we're halfway done. But in the case of Deepwater, the BOP intervention did not work. There was a problem with the BOP. So we still have oil coming out, and we're on day 2, 3, 4 right now. So what we can do very quickly is to take a couple ROVs now and do the next phase. Is if we still have oil coming out, we do subsea dispersant injection. Now when we fly and spray oil on the surface, we're targeting and maybe getting something on the order of 80 to 90% dispersant on the oil. If you're down at subsea, you're putting the dispersant wand right into the plume, so you're getting 100%. And again, by knocking down the dispersant here, forming small droplets, gets slower rise, more dispersion into the water column, we improve the VOC atmosphere above. So this could happen on day 3 or 4, depending on how far out the well is, and we have enough dispersant to continue this operation while we're getting the capping stacks ready. Again, on the surface, other things can happen, be it more dispersant, in-situ burning, which was used extensively in Deepwater Horizon, and by day 3, 4, 5, 6, you're starting to get your surface mechanical recovery capability going and deployed. But there's a lot of logistics to this, and some of the wells out in the Gulf of Mexico are almost 200 miles out. So it's a long way out, and you saw from that other slide a limited capability to recover oil. This is one of the capping stacks that we have in Brazil. We're an international organization. Our capping stacks are in Brazil, Norway, South Africa, and Singapore. I'm using this as an example. There are 2 organizations in the Gulf of Mexico that have their own capping stacks, and they're based in the Houston, Galveston area. But these things are huge, and the mobilization and deployment of them takes some time, maybe 2, 3, 4 weeks. So we have a couple different types. There are a few different kinds in the Gulf of Mexico. Again, this just gives you some sense of what we're talking about. We can also fly our capping stack somewhere, and then there's the problem always is trying to get a vessel, which is not a hard thing in the Gulf of Mexico, but in some other parts of the world, to get a suitable vessel with a suitable crane is quite a challenge. So then this is what it would look like with the subsea tree here and bringing a capping stack down. Now, when we bring a capping stack and land it on the top of a well that's lost well control, all the flanges and valves are wide open so that the oil goes right through the capping stack. And what we do then is, there's 4 different chokes on it, and what we would do is slowly choke down, and this was a big concern during Deepwater Horizon, was do we have well integrity? If you just put it on and closed it, it's possible that you would have oils coming up through the substrate. So we put it on with chokes open, and then very slowly try to choke down on it, and at the time keep a look at the well pressures and well integrity. If you have good well integrity, then we can shut it in, and then the relief well and permanent shut-in will go on. If you don't have good well integrity, we have a system called containment and flowback, where we would actually go from the well. We'd set up a number of, we can actually do 3 legs to actually bring the oil back up to ships that can treat it up in the surface. So that's kind of the look at how this would go. This is the containment part. Again, you can see there's quite a few ships required. We call this simultaneous operations because there's a lot that goes on at one time, including the surface response, which is more conventional. So this is just some of what we sent to Deepwater. Now, in terms of science, my organization gets involved with science. We sponsor some, we're involved in some of it. The Tropics experiment, Brad and Abigail Reniger and I were down there a couple years ago doing some data collection. We've been involved in a number of things, but one thing I'm involved with is taking what we call a counter-historical look at Deepwater Horizon. And what we're looking at basically is 2 things. What would have happened, and we have a bunch of different cases. What actually occurred in Deepwater Horizon, and that's to the best effort to model it. And then what would have happened if we didn't use any dispersant? What would have happened if we used no subsea dispersant injection? And Deepwater Horizon was the first time subsea dispersant and injection was actually tried. So we have these 6 different cases, and we're modeling the physical or the mass balance, where did the oil go? And then we're taking a look at what additional or resources would have been impacted. So this study is ongoing right now, and we're hoping to conclude it at the end of the year. So it's a lot of modeling, but really 2 dimensions. If we didn't use dispersants, what we're expecting to see is the extent of the slick impacting the shoreline would be greater, and consequently the impact on sensitive resources would have been greater. But it's all, some of this work is turning on the model and letting the computer sit for a week and run through. So I think this is going to be a real interesting thing to take a look at. I just want to mention that after Deepwater Horizon, the industry got together and said there were 3 different areas they were looking at. One is what can we do for prevention, what for intervention, and what for spill response. And these have been multi-million-dollar projects by the international oil and gas industry. For oil spill response, it came up with a number of good practice guides, which include strategies, response, preparedness, and impacts. So all of these are available, here it is again, in a number of good practice guides that are available online. There tend to be fairly deep studies on all of these, but if you want to know much about how the industry is going to approach oil spill response, these are where you can learn. This is what we call the tiered response wheel, and this basically shows 15 different areas that we look at when we do a response or when we plan for one, and there's pretty much a good practice guide for each. Dispersants, logistics, waste management, shoreline cleanup, the whole gamut. And so they're very available. I would say that the work that the Sea Grant folks do, I think they're universally recognized by academia, by regulators, by industry as really, really excellent work with the synthesized science. And that's generally what we do. I would say one thing when it comes to science. I'm going to be at a workshop in California in a few months on science and response with NOAA. And when it comes to science, we're willing to listen to just about anything, any science, any technology before a spill in the preparedness side. When there's actually a spill, it's now we're going to go into the response mode. And the idea of taking on all kinds of new ideas is just not going to happen in the first 3, 4, 5 days. It becomes a long-term thing, but then we're going to look at additional new methods, new science. But for that first week, everyone's in the crisis mode and it's probably not going to bring in new ideas at that point. So I will close with saying that one of the things science does, it gives us good answers to problems that may seem obvious something else. And this is the 1993 oil spill right on St. Pete Beach here. My folks live in Tierra Verde for 43 years. But one of the things, this looks really bad right on the beach, but it's actually, as someone pointed out earlier, it's not as bad as if this oil got inside Tampa Bay and into the mangroves. And I think Brad was involved with getting some of that oil out of the mangroves during this spill. So yes, this looks terrible, but there are other things that could have happened that would have been much, much worse. So that's science telling you. On a fine sand beach, that oil doesn't go very far down. It was thick oil, and so it was relatively easy to clean up compared to oil that got into Tampa Bay, into the mangroves. So that's it. Thank you for your time.